on data-driven optimization in pricing and revenue management. I'm Victor Araman, and this is organized by the Center of Advanced Mathematical Science and the Al School of Business. It's run by Arnoud and Boer from Amsterdam University, and this is the second session out of 3 sessions. Go ahead, Arnoud. Thank you again.
Yes, thank you, Victor, and welcome everybody to this Zoom session, to the second session of 3 indeed on data-driven revenue management and pricing. So again, just as last time, if you have a question, feel free to unmute and ask, or if you prefer, you can put it in the chat, and then Victor at some moment will inform me, because I cannot see the chat directly. Okay, brief refresh what we did last Monday. So there we considered a very simple model with pricing and learning. And the goal was, in a sense, pedagogical, to introduce some notions. What is going on when you want to learn the optimal price? So we considered a setting where, for example, there are no inventory restrictions. Demand is a linear function with just 2 unknown parameters that we try to learn from data. Or to be more precise, we do not try to learn them from data. We try to earn money. And if we happen to also learn some parameters, that's nice, but that's not our primary goal. Our primary goal is to earn money, and not our goal is not statistical in nature. Now, we saw that the most natural policy, certainty equivalent or greedy, performs very poorly. If you always do what seems best at the moment, give your data, then you don't learn. Because you have to experiment, you have to actively deviate from what seems best. Now, what is best and how good is a policy is measured by its regret. That's just its deviation from what is optimal. So the cumulative expected loss over T time periods. You want that to be small. If it's order T, then that's not a good thing. And then on average, you keep losing every time period some money. And if it's slower than T, that's good. And you want this rate to be as small as possible. We look at regret rates because we cannot really compute an optimal policy for any given finite T, except in very simple settings. So we know that our policies have like regret close to square root T, and that is the best possible. Now, that was previous lecture. Today, I want to discuss what is emphasized in red, namely the inventory constraints assumption. And also, I want to spend some time on the modeling aspect, because we assume a parametric model, and you can say, well, can't we just do it non-parametrically, because that's much more general. Now, and in between, I suggest we have a short break. But before the break, I want to discuss the inventory setting. Because revenue management, of course, originated within the airlines industry, you have a finite number of tickets during a finite selling season that you want to sell. So the price depends on how long it takes before the aircraft departs and how much tickets you have left. So this is not just some fancy item that doesn't really matter. No, this is a crucial aspect of your problem. And we will see today that indeed it has a very interesting influence on your policy to learn. Now, the first model that I want to discuss is by a paper by Bespes and Zevi, a very influential paper from 2009 that generated a lot of follow-up research. And let me just discuss and introduce first their model. So they have a continuous time model. So the sales horizon is all time periods between 0 and T for some capital T. And there is an initial inventory of X products. X is actually a natural number. So at each real T in our time horizon, we determine a price in some feasible interval. And there's also some price P infinity, which is the shut-off price. That means that if you use this price, then the demand will be 0. So that's just a modeling device. You could, in practice, you can just not offer your product on your website. That's basically what you would do. That corresponds to charging price P infinite. Now, customers arrive according to a Poisson process. That means that the time between customer arrivals is independent, exponentially distributed. The parameter is lambda of PT. So PT is my price, and lambda is then of the demand function, some unknown function. So typically it's like continuous and decreasing in price. It satisfies some regularity properties. For example, usually what is assumed is that it is sufficiently often differentiable. And what we also assume is that this function is concave. So we do not assume if a function is concave, then it's easy to maximize. We do not assume that the revenue function, so price times demand, is concave as function of price, but it's more common to assume that it is concave as function of demand. So if the demand function is 1-to-1, it has an inverse, so P. So then I can, instead of controlling the prices, I can control the demand rates. I choose a demand rate, which has a unique corresponding price P of lambda, and that this function is concave. Now, it turns out that for many of the models used in practice, this function is concave, but usually revenue is not concave as function of price. It is concave if your demand function is linear, but for many other settings, it is not. Okay, so that are just some regularity assumptions. Now, then the problem is as follows. We need to determine a price, so P of S, for each time point S. It should be non-anticipating. That means each price can depend on my history of demand and price observation, but not on the future. And my goal is to maximize revenue. Now, to formulate that, so we have here our demand rate as function of price at time point S. So the total demand is Poisson. You can write this as this. There is like a unit rate Poisson process N, and then my demand at time T is N evaluated in the integral, in this integral. And then my revenue, that's here, that's what I earn. I take the expectation of the integral over my time horizon of my price whenever there is an arrival. So that's this D N of S. And the constraint says that you cannot go out of, you cannot sell anymore if you're out of stock. So basically that means or is equivalent to the condition that when you're out of stock, inventory 0, then your price should be the shutoff price. That's the same. So we want to maximize this. That means for each possible, so under full information, if I would know this demand function lambda, that would mean that for each possible state where I'm in, I need to determine the price. So what is a state? A state is how much inventory I have and how much time I have left to sell my inventory. Now, the quality of my price process, so for each state, I give a price. That gives me some expected earnings. And I want to make that as big as possible. So as big as possible is this. I maximize my objective J of pi prime. So pi prime is here my policy. That is the abbreviation of the price process. And my loss is the difference between the best possible earnings and what I actually earn. Now, this is nice. Small problem is that this is difficult to evaluate. It's difficult to compute, for example, if you have multiple products. In this case, it's not so difficult to compute. You can just discretize your state space. For example, you make small intervals, small time intervals, and then you can run a backwards recursion and you can try to compute the optimal prices. But this doesn't generalize well to multiple products. Then you get a high dimensional state space. That's called the curse of dimensionality. You cannot really, by brute force, compute this. So that's a pity because we want to learn. And we want to learn the best possible policy. But then, of course, we want to compare it. We have a policy. How good is it? Well, we need to compare it to the best possible. and then we cannot compute that. How do we solve this? Well, we compare it with something that approximates this thing. And that approximation is a deterministic approximation. Now, this may have been shown already in one of the earlier lectures, but I just repeat it for those of you who were not there. So, demand is random. Customers arrive and then they buy something or not. If you remove the randomness, then you get the following problem. I have to set my prices at each time period between 0 and t. That generates demand, lambda of P of S. So my expected demand is this integral. And so here P of S is my decision variable. And the constraint is that I cannot sell more than my inventory. So this is my expected demand. That cannot be more than my inventory. And of course, prices should be in the feasible range. Now, this is a deterministic problem. There is no randomness anymore. All randomness has disappeared. I just assume that instead of randomly arriving customers, there's a flow. I set the price and that induces a flow of customers. And if price increases, then the rate decreases. Now, this problem is actually very simple. The optimal price is just to use a fixed price. Now, what is this fixed price? Well, it depends. You can imagine if you have sufficient inventory, well, then you just want to maximize this inner quantity price times demand. Set the price that maximizes this. And if you have really limited inventory, then you want to make sure that you run out of stock exactly when your time horizon ends. Not too early, because yeah, then if you run out of stock too early, then you could have maybe increased the price a little bit. And if you run out of stock too late, so you don't run out of stock at all, then maybe you should also have altered your price. So this is already shown in the Gallego and Van Rysing paper from 1994, the optimal price. So it's interesting, it's a paper about dynamic pricing. And then a nice result is that asymptotically, there is no dynamic pricing, just static pricing. The optimal solution is this PD, which is the largest value of the unconstrained price that maximizes my price times the demand function. And the constraint or the clearance price, which is the price such that I run out of stock. And so if I have lambda P times T, that is my demand in expectation in T time periods, that should be equal to X. So equivalently, I want this to be as small as possible. Now, so that is the, if I know lambda, then it's complicated, but I have a good approximation, just a fixed price, whatever my state of inventory is. Now, why is this useful? Because first, this is easy to compute, given that I know my demand function. And second, what I earn if there is no randomness is an upper bound to what I earn if there is randomness. Randomness doesn't help you as a decision maker, as a seller. It makes it more difficult. If there is no randomness, everything behaves as it would be in expectation, then you earn more. You can show that by analyzing the dual of this and exploiting concavity of the revenue function. Now, so I said we want to define regret, and regret is complicated because this object here on the left, we don't know what it is. So what can we do? We just replace it by our deterministic upper bound, which is easy to compute. So we can define the regret of a policy as the difference between this, what you earn in this fluid limit or deterministic upper bound, minus what I earn under my particular policy by. Now we also scale, we divide by this j day so that we get values between 0 and 1. That doesn't really change anything. Now, and we also note the dependence on inventory, time horizon, and lambda. Now, this fluid limit is not just some upper bound. It is if inventory and the length of the time horizon grows large, then you more or less approach this. Now you can show these kinds of bounds. And you can imagine that this makes sense. If you really have a lot of inventory and you have a large time horizon, well, then you can fluctuate your price, but in the end, the randomness doesn't matter that much anymore. A fixed price is okay. And you can show this and even show bounds. So this is not just some unattainable upper bound. No, this is really roughly what you can get if both inventory and time horizon are big. Now, this is nice because that means that instead of some complicated policy, all we have to learn are two numbers, PU, the unconstrained optimal price, and PC, the clearance price. And that is much easier. Now, that's one of the key observations in this paper. Of course, there's a lot more that's being done, but that is the key idea underlying how you learn this. So here's a simple policy. So the policy is as follows. We start with an exploration period where we just try several prices. So which prices? Well, you see we make a kind of grid. We start at the minimum feasible price, and then equally spaced intervals, we go to the maximum spaced price. Each of these exploration prices we use for a while, say tau over kappa, which are some problem parameters, policy parameters. Of course, we always switch to the shutoff price if we're out of stock. Now, then we have our data. Then we look at the demands that we observed, and based on these, we can estimate the unconstrained optimal price and the clearance price. Now, I haven't put the formulas here, but that's not very complicated. There are several ways to do it. One is just like for this one, you can just look at what you actually earned. And for the clearance price, it may be that there is no particular price that exactly approximates, that exactly is the clearance price, but you just choose the closest one, something like that. Yeah, such that the difference between your remaining inventory and zero is as small as possible. Now, with these estimates, in the remainder of the time horizon, we just use this estimated, the maximum of this fixed price. That's it. Now, let's talk about regret, because that's how we measure this. Well, it only makes sense to talk about regret if this is a good policy. So if this deterministic upper bound is really good, is close to this guy. So that's the asymptotic regime where we will study regret of this policy. Now, there are actually at least two different regimes, and there can be many more. So the regime in which this regret rate is studied is the following. There is just a single selling season, and the inventory and the demand function grow large. Now, you can, the inventory and the demand function, what does that mean? I just multiply my inventory by some number n, and I multiply my demand function by some number n, and then I have the nth problem instance, and then I let n grow large. It's the same to having the inventory and the time horizon grow large, and having just you multiply t by n and x by n, and fix your lambda. That's the same. Now, that is one regime where you can study. So we have seen last Monday that we let t grow large. That's motivated by the fact that time periods are usually small, and we want to look at asymptotics, because otherwise we cannot really evaluate policies. But in this case, we do not only let t grow large, we also let the inventory grow large, so that the randomness, the influence of randomness disappears, and we can just, we have this, that only the fixed price, PU or PC, is what we need to know. So this is useful in an application where inventory is large, a big cruise ship or a big aircraft. Now, in a few slides, we will also study another asymptotic regime where t grows large, of course. but inventory is bounded. So that means that we will not consider one single selling season, although that's also interesting, but multiple consecutive selling seasons that just repeat. So you repeat your selling season, and at some moment, the season finishes, and then you start a new season. Okay, let's study the regret in this first regime. Or I said study, but due to time constraint, I just give the results. So the regime is we consider a sequence of problems. And in the nth problem, so n is a natural number, we have the inventory is some x times n, and the demand function is the original demand function times n. Now, if you do that, then there are two results in the paper. Let me start with the upper bound. So this policy that I just showed, this simple policy that just divides the time horizon in two phases. First, you explore with prices, then you estimate, and then you exploit the knowledge that you have. This policy has a regret of n to the power minus 1/4. So remember, there were these parameters tau and kappa related to how long you explore and the distance between consecutive exploration prices. Now, if you tune them in the right way, you can show that this regret achieves this rate. Now, remember that here the regret is the relative regret. So, because we divide by this JD. So this would be n to the power 3/4 in the usual, the absolute cumulative regret. Okay, so that says how good this policy is. Is it asymptotically optimal? So unfortunately not. Or at least we don't know. There's also proof of a lower bound that any policy, or to be precise, any sequence of policies, because the policy can use as input, say, the initial inventory. But any sequence of policies has regret, relative regret, at least a constant times n to the power minus 1/2. So this was a very influential paper which generated a lot of follow-up research. And of course, the obvious question is to close this gap. Now, in 2014, the paper by Wang Deng and Ye was published, which is also called Closing the Gaps or something like that. And they showed by a more refined analysis that a different type of policy can achieve the optimal rate up to logarithmic factors, which as before we do not really care about. We should, but you know, we have to be friendly for ourselves. If we get the right rate apart from logarithmic factors, that's already nice. Now, as I said, due to time constraints, I do not have time to go into the details, but basically you can imagine what you have to do if you analyze for this case. What you have to do is, I have my exploration prices, I have estimates, I need to have a very good understanding of the quality of my estimates. Last time we talked about least squares, ordinary least squares, and then we need good convergence rates. Same here. If you estimate something in data-driven problems and you want to analyze the regret, the key ingredient is a good understanding of how good your estimates are. Now, and the same holds for the more involved policy that has the right regret rate. So apart from the technical questions, what do we learn from this? We have this problem, the classical dynamic pricing problem in the revenue management literature. It's complicated because we don't know or benchmark in the full information. And the solution is, well, if your inventory and your time horizon are large, then you do know your benchmark, just a fixed price policy, because it's a fluid limit, the randomness disappears. Then it's easy. You just have to learn the optimal fixed price, which is a number instead of a policy, high-dimensional object. Now, and then because it's easy, we can analyze it and the optimal regret rate can be determined. So what can you remember from this? The key trick is basically this, that we study a particular case where the fixed price policy is a reasonable benchmark. Now, let's now go to the second asymptotic regime, and that's based on a paper from myself, motivated by the fact that I thought, well, yeah, so very close to my house, there's a very, very small shop where they sell flowers. And I was thinking to approach the seller to do some revenue management or auction theory. And then I thought, well, this asymptotic regime is not really applicable to his flower shop. So what should he actually do? So I was thinking about that, and that was one of the motivations to think about this. So another regime, we have multiple consecutive selling seasons. Like he goes to the flower auction, yeah, each like periodically, and you have many other applications where inventory is replenished periodically. Now, that is the key. And the inventory, it doesn't scale, it just fixed. Now, so the selling season just restart. Now, to begin with, we assume that these selling seasons all have the same initial inventory, the same duration, but you can extend it that this can be different. Now, and they are consecutive. They can also be overlapping, but that just complicates the notation for this presentation. So let's assume they do not overlap. Let's see what happens then, because then something interesting actually happens regarding learning. Now, first, we observe that inventory is not large, so the effect of randomness does not disappear. We really have to compare our policy with the solution to the Markov decision problem. We cannot escape that. But actually, that's good news, because the randomness that we have will help us to construct a policy that's very good with regret log t, or actually the square of the log of t, which is much smaller than square root t. It's so so a regret rate. Now we have seen already a couple of regret rates, square root t, or things like that. A regret rate is a kind of classification how difficult it is to learn. And log t means, well, it's much easier in a sense to learn in this problem than in the original problem. Now, how does that work? Now, in this case, we have a discrete time setting. We have seasons, they have length capital S, and they are consecutive. So the end season is these time periods. Now, the initial inventory at the start of the season is some X naught. And then the next inventory is the previous inventory minus the demand positive part. dt is the demand. Now, as always, the seller determines a price, which should be non-anticipative. It cannot depend on the future, but only on the past. Demand is Bernoulli, and it has a particular distribution. So the probability that you sell something given that there's inventory is some generalized linear model. So what does that mean? It is some function of something that is linear. So a standard model is the Bernoulli logic model, where d is the logic function. So you can use that. But if d is the identity, then we just have a standard linear demand model. So theta 1 and theta 2 are unknown parameters. Now, of course, if there's no inventory, you have no demand. These are unknown. They lie in some compact set. And we can estimate these guys with maximum likelihood estimation. So the problem is quite similar to what we discussed Monday. Only the difference is that now sometimes we go out of stock, and when the season is finished, we replenish. But we again have a parametric demand model, which in this case is probably essential, as I will explain in a minute. And there are parameters that we don't know, we want to learn. Now, Let's first go to the full information solution. That is our benchmark. As I said, there is no fluid limit in this case. We just have to solve the Markov decision problem. You can do that by backwards recursion. So there is a state, that is how much inventory do I have, X, how much time periods do I have left, and then there is this Bellman equation, the optimal revenue that I can earn from this state, X, S. Well, what is it? I need to choose some price, then with probability D of this. With this probability, I sell something. Then I now earn P, and in the future, I earn this quantity. The optimal thing I can earn when I have 1 unit of inventory less, and I'm 1 time step in the future. And with this probability, I don't sell anything immediately. So I only have my future reward, which is V of X at the same inventory in S+1. You can solve this. You just start at the boundaries and then you go back. So you can compute this matrix if you would know theta. And that gives you a price for each state. Now, under some conditions, this is also unique. So I get a unique optimal price. Okay, so if I know the parameter, then of course what I should do is always chart this price. It's time period T. What do? I look at my current state, my current inventory, and my stage in the selling season, and I look in my lookup table and I chart this price. Now, that will be your benchmark. We don't know, of course, data. So what do? Now, what is interesting is the following. Last Monday, I tried to convince you that you need to experiment, but otherwise you cannot learn. But now I will claim that you don't need to experiment at all. Why is that? Well, so we have some estimates, say theta hat. Suppose we during a selling season, we just use the prices that are optimal given this theta hat. And so I have my states, they can be random, but in this season, I just use the prices that are optimal given this theta hat. Well, the thing is, we're not in some fluid regime. The optimal price depends on your state. If you just have 1 period left and you have a lot of inventory, then it will be very cheap. But if you have many time periods left and just 1 unit of inventory, then you can make it very expensive. You have many opportunities to sell it, and you just 1 unit. So, you can make it large, the price. So that means that there is a natural variation induced by the problem. My price sequence for all time periods where I have inventory, because that's the only, otherwise I don't sell anything. The variance of this price sequence is bounded from below by some number that is independent of my estimate. Now, that's of course very nice. There's endogenous price dispersion. I don't need to experiment. It goes automatically. I can just learn on the fly. I can use a greedy policy. Now, how nice is that? Now, note this assumption is crucial. What is this assumption? The initial inventory is more than 1. Because if I have just 1 unit of inventory, it can be that I sell it immediately. Then I've just used 1 price and the variance is 0. And the inventory should be smaller than the number of sales opportunities. Because if I have more inventory, I have a Bernoulli demand model. So then basically it means I have infinite inventory. I can just, I can never go out of stock. So in that case, there's no endogenous price dispersion. Then we have to experiment. But when we're in this regime, then it goes automatically. I think that's nice. And it also means that you can just use a certainty equivalent policy. So what do? We have some estimates. In each season, we just charge the price that is optimal given our current estimate, data head in our current state. And when the season has ended, we update our estimate of data with maximum likelihood estimation. Now you can then, we know that the variance has some lower bound. So similar as this least squares convergence rates, you can have similar maximum likelihood convergence rates. Now you can show that the expected loss in a season is bounded by the mean square error. You can analyze these by concentration inequalities, and then you can show that the regret after t seasons is order squared of log of t, which is much smaller than square root t. Now, I also showed the lower bound. I cannot really get rid of this squared. There are always logarithmic problems in this data-driven problems, but we don't care about that too much. So what do we learn from this other asymptotic regime? The key issue is that now inventory is bounded. We have a generalized linear model for our demand. We cannot use some fixed price heuristic. They don't work. But there's something else that suddenly happens, namely endogenous price dispersion. And we don't need to experiment. We can just use a greedy policy. Now, I said, so we use, maybe that's nice to emphasize. We use a parametric demand model, in particular a generalized linear model. The demand is some function of theta 1 minus theta 2 times price. Now, after the break, I will talk about model selection. But in this case, you may wonder what happens if I would adopt a non-parametric approach. I don't know, but I think that I'm not sure if you then can reach a logarithmic regret. Why is that? Oh, we have some variation in our prices. Now, if you think about linear regression, I try to fit a line. The line is just y is a plus b times x. If somewhere here I have some x's, some prices, and they have some variation, but later on, in a completely different region, I want to charge an optimal price, that's okay. I just have the quality of my estimates, and they are uniformly good over my assessing. But in a non-parametric approach, that's of course not the case. Then we don't have this. So it's basically the difference between local and global. In a non-parametric setting, if I have here my prices and I have a lot of price dispersion, nice. That means that locally I have a good estimate of my demand function. But somewhere else I don't have. I cannot just generalize that. So I still maybe need to experiment or not. A nice open question. Okay, well, that closes the first topic that I wanted to present to you. Pricing and learning when inventory is bounded, based on the Best Savvy paper and a paper by me and Bert Zwart. Maybe we can have time for questions if they are, and after that we can have a short break before we start with the second topic. But are there any questions at this moment? So if not, then I suggest we have a brief break, say 10 minutes to get some coffee, and then I suggest that we continue, 5 before 5 local time, so in roughly 10 minutes.
Okay, let's do that.
Yes, so welcome back, everybody. in this second part, I want to talk about model selection. We have seen already the problem, or we have seen that that you can have parametric models or non-parametric models. And then you may wonder, well, why do you study such a specific case? You run the risk of model misspecification if you assume that the demand function, for example, is linear. Why would you do that? Can't you just develop techniques without this restrictive assumption? Well, that's of course a valid question. So I want to spend some time on this. Now, the question, should a model be parametric or non-parametric, like a demand function, is basically part of a bigger question. Should you use a simple model or a complex model? Whatever your model, there are always things that you did not include in your model. Like usually noise terms are not correlated in many demand models. Things are stationary, parameters don't change over time. All kinds of factors are not incorporated. Now, there are good reasons for that. One of the reasons is explainability. Like if you have a price manager in practice who understands that you fit a line, but to get a demand curve, but maybe he or she doesn't understand kernel density estimation, well, then it maybe is helpful as a first step to use a parametric model. But that's nice, but you can also think about this from a performance point of view. And if you're interested in earning money, or in general, in maximizing your objective function, then the question is, yeah, which model generates the most money? This is, I think, an extremely relevant question. Also in general in data-driven problems, but also in revenue management, data-driven problems. You can, for example, have assortment optimization with many products. Then is the question, what is a good choice model? There are really, the most complicated models, or should you use just something simple? Now, as I said, you can just have the canonical dynamic pricing, as we discussed for the break model, where arrivals are not independent but dependent. Now, then your problem really becomes very complicated, because these dependents, you can have basically any structure, whatever you want to allow. Pricing with high dimensional covariates is another example. Covariates are properties of the products and or the customers. Now, usually you know a lot about your products and about your customers, so you can include all kinds of information. But how does the demand depend on all these covariates? Yeah, should you just assume some general non-parametric form, or something linear or quasi-linear or semi-parametric? That are crucial questions in theory, but also in practice, of course. Now, what I want to discuss is how model selection depends on your data quality. Now, there is some recent empirical work. I want to mention two papers. This is a recent paper by Regularization and Vulcano. They compare many choice models. Well, as you might have noticed in the previous two sessions, there are really a lot of ways to model how people choose. And in revenue management, that's very relevant. There is a number of products, the assortment, and people select usually one out of them, or at most one. Now, and the probability that you select something from a set that comprises a choice model, there are many variants. Now, this is a very nice work that just compares different models: Markov chain, MNL, nested logit, mixed logit, exponomial, and some others. The statistical performance. So it's basically about estimating, say, a choice probability, predicting. Now, and one of their conclusions is that the exponomial model is good when there is not so much data, and the Markov chain model is good when there is more data. Now, this already shows that your data size matters. Another recent work is by Feldman et al. And I like their outcome a lot. So they have really done a field experiment. It's not just some simulation, now a real experiment at Alibaba, a very large online seller, of course. And they compare, so it's about product display optimization. Now they have two sophisticated machine learning approaches, and they have our good friend, the MNL model. And they're going to compare the performance in terms of revenue. So not in terms of prediction, or actually they compare both, but also what you earn. Now, it turns out if you care about the prediction of purchase probabilities, MNL is not so good. The machine learning approaches do much better. But if you look at the revenue, then they have two machine learning approaches. The MNL is just much better than one of these machine learning approaches and is equally good with the second approach. It's, if I remember correctly, it's even slightly better, but it's not a significant difference. So in terms of revenue, just throw away your deep learning algorithms. Our good friend, the MNL model, is good enough. Now, I was really surprised by this finding. And I mean, in academia, we use the MNL model as a standard model. If you have something, if you have a paper, you want to, I don't know, you want to investigate something, some property of choice models, some new viewpoint, the first thing you do is let's try the MNL model, see what happens then. Well, it can feel a bit academic and non-practical, but well, this suggests something else. Now, the big question to which I don't have an answer is, we see that the model is hugely important. So we also basically want to not just stick to one model, we want to data-driven, in a data-driven way, determine which model is better in terms of revenue. Now, is that actually possible or not? Now, I don't know. I've done some work to think about this, which I want to share, but we came up with a setting and a model and a solution. I mean, I don't claim that the solution is particularly good, but this is just more meant to share the questions instead of the answers. Yeah, so the setting is as follows. We have some function that we try to maximize. It's a function, reward, of our decision, x, and some randomness that depends on x. So say x is our assortment, yx is the demand, something like that. We don't know the distributions. Suppose they have common support. And there is data. So the data is our previous decisions and corresponding observations, now, which come from the corresponding random variables that correspond to the decisions. So you can think of it as this is a price or an assortment, and this is the corresponding purchase. Now, a model is a collection of distributions that these random variables y can have, which I just basically identify by a parametric data in some set. That doesn't mean that this is parametric. This can just be a non-parametric set. So this can be this, the set of all distributions on the appropriate support. Now, then we usually have an estimator that maps data to some estimate. So given some data sequence, this object in this set, we apply our estimator tau. The n indicates the data size, and we get, or this should just be in theta, and we get a value of theta. Now, that is an estimate of the distributions, and then we usually have an algorithm. And the algorithm maps an estimate of these parameters to a decision. So data, model, estimate, and algorithm are the four ingredients that you need for data-driven decision making. Now that's just the function chi. It might be a maximizer. You want to maximize this function. But it doesn't have to be an exact solution. So if you think about choice models, you have some assortment and a corresponding purchase probability. If your model is, say, mixed logit, yeah, then the optimization problem can be NP hard. So even if I have some estimates of all the involved parameters or distributions, I cannot compute the optimal assortment. So this chi is not exact, it's just some approximation with an approximation error. Now that's of course important, because more realistic models often have this property that the optimization becomes more involved and you get an additional optimization error. So you have either a simple model with a model misspecification error, or you have a complicated model with an optimization error. But that's not all. There's also the statistical error that plays a role.
Just quick question, Arnoud.
Yes.
On the model set, what does it mean when it's non-parametric? How do you define it?
Yes. So then, yeah, this is just a label. So then theta. So suppose this is just capital theta can be the set of all distributions on, say, a dual line, and then theta is just this distribution. So it's a bit confusing notation. Then you identify theta with F, say.
Oh, I see. So it's some kind of. So theta would be the set of distributions.
Yes. Yeah. This is just.
Okay. No, it's okay. Fine.
Yeah. Okay. So we have now we look at multiple models. Say the simple MNL model, or the complicated machine learning model, or MNL or mixed logic. Now they can of course have different parameter sets. Often the simple model parameters is a subset of the big one, but that's not always the case, because very often a simple model is just a complex model where some things are zero. That's not always the case, but very often it is. Now, and then the second question, if you think about the performance of these models, is whether the most complex model is actually correct. Now, in practice, of course, it's not. It doesn't matter how complex your model, there is always an error, because reality is more complex than any model. But if you think about performance, we assume that this is correct, because that is our benchmark, basically. Modeling errors of the most complicated model that we have are much more difficult to analyze without, I mean, if you want to think about the modeling error of the most complex model, you need to assume something about the data generating mechanism. And what do you assume? So we assume for now that this is correctly specified, without saying that thinking about the misspecification of the most complicated model is not important. So that means there is some true parameter data stuff. Simplified model might be misspecified or not. Now then we have our data. In this case, we have two estimators for each model. And we have two algorithms, chi-k. They might be exact. That means they optimize some objective function, or they might be approximations. So that means that we have two decisions, say two assortments under an MNL model and under a mixed logic model. Oh, then we want to know which one is better. Now, the question that I just want to pose without knowing how to answer it is, can you determine which one is better given given some data, some arbitrary data set? And how do you do that? Now, that's the question of decision-based or performance-based model selection, because we don't care. There are many criteria for model selection. ICA's information criterion, there's a lot. But in the end, you just want to maximize your earnings. That's what you care about. So we have these two decisions. Let's call them XK. They are the data set, and then we apply the corresponding estimator, and then we apply the algorithm. Now, we evaluate these decisions, assuming that the most complex model is correct. As I said, that's not the case, but otherwise I don't know what to do. So what we do now is we say, well, suppose that the mixed logic is correct. Is then MNL still a better ID than mixed logic? Something like that. So we have these decisions. Well, so R is my objective function for the most complicated model. Now, it depends on my decision, say my assortment and my estimate. Now, this is what we want to know. Which decision X of K maximizes the true reward? The problem, of course, is we don't know theta star. Now, usually what you do when you want to estimate something, you replace what is unknown by an estimate. So you can say, well, I don't know this, so I replace theta star by my estimate, say, under the zero model or under the simplified model. This, of course, doesn't work, and you probably already know why. Because, I mean, if I don't have any optimization errors, then the decision under model 0, the more complex model, is by definition a maximizer of this function. So yeah, then it's, I mean, this is always better or equally good as the decision under the simplified MNL model. So we cannot do that. Now, there are several things you can do. You can split your data and use some kind of cross-validation method. Closely related is a bootstrap procedure, which we propose in this paper. How does that work? We have our data set. We have our estimate. So we say have mixed logic. Then we draw a new data set with the same initial decisions, but with new purchase decisions. And based on this new data set, we estimate again the parameter, and then we evaluate the decisions. So this is a bootstrap procedure. You can also do something else, kind of cross-validation. Now, again, I don't claim that this method is good. What I like is that this is an attempt to do something generic. I talk about MNL and logic as an example, but this is a very broad framework. Yes. So in very simple cases, you can do some analysis on the quality of this model selection decision rule, but in general not. I see there is a question by Yuri Fonseca. Is that right? Please go ahead.
Yes. Can we see this problem of decision-based model selection as some sort of bandit problem with expert advice, or and try to use some of these tools?
Yes, that's that's a good question. So then you get a kind of meta bandit, because we have already a data-driven problem, and then we have two experts who, based on the same data set, try to say something about the best decision. So it is a kind, you can also see it in this way indeed. So in this formulation up to now, it's not dynamic, it's just static. There's a fixed data set. But in a few slides, I will also mention that you want to do this in a dynamic way. As your data increases, at some moment, you want to switch from the simple model to the complex model. And the question is when. So that's thanks for the question.
Okay, thank you.
Any other questions? Yes, so as I said, it's complicated to analyze the quality of, say, this rule, or you can also invent other rules. To give some intuition, I share some numerical work. So on assortment optimization with synthetic data. So in this case, we have some assortments, and we have the simple model is an MNL model, and the complicated model is a non-parametric choice model. Now, here you see two tables of two experiments. In the left table, the ground truth was MNL. So the simplified model was actually correct. Now, in that case, of course, you want to use simplified model. So you see here, N is the size of the data. Opt is the optimal amount of money that you can earn, 40.44. You see that if you follow the MNL decisions, then you converge much quicker to 40.44 than if you follow M0, the non-parametric, because that just has a much larger variance. Like here, if N is 100, you see that M1, the MNL model, is a very, very close to optimal. The non-parametric model is far away. And this procedure is somewhere in between. It captures some of the gain that can be captured by the MNL model. Now, the MNL model, M1, can also be misspecified, like you see in the table on the right. Then here the optimal assortment gives 68.98 money. But you see that the MNL model, the revenue converges to something else. Now, and the rule that we proposed, the decision-based model selection rule, detects this and also converges to the optimal revenue. Especially for small data set, sometimes it will select the MNL model, but later on it will not do that anymore. Now, I don't make any claims about generalizability or anything else. But this shows some things that happen. So the problem is, yes, I mean, how do you evaluate a model selection method? That's not so easy because the quality depends. It just depends on what is the ground truth. And yeah, do you want some worst case? Or in reality, you just want, you maybe don't care about the worst case. You just care about what's actually going on. Many questions. I think that this is a bit, this topic deserves more attention, but it's complicated, or well, I find it complicated. But I think it's a very, how to say, it's a very fundamental question, the quality of models, and see them basically also as decision variables. Now, maybe it's good to know regularization is also a kind of, that is one of the model selection methods that happens a lot. You have regression, you have many parameters, and you just assume, for example, that many of them are just zero. That's one kind of regularization. There are other kinds. And as you get more data, you allow more variables to be non-zero. And in general, and that relates to the question by Yuri Fonseca, you want to have model selection that is dynamic. Maybe you start with an MNL model, and then at some moment, and the question is at which moment, you switch to something else. I think that's a nice topic, but it's also challenging. And I don't know if something theoretical can be done there. Now, in the maybe if there are any questions on this topic, this is a good moment to ask, because I will now switch to a different but related topic.
This is, I mean, obviously, also it relates to Yuri's point, but the ranking and selection, to some extent, literature is similar to that, right? Where you have number of specified models and
yes,
or simulation, and you need to pick kind of like rank them.
Yes, it is related to many streams of literature, including the ranking and selection literature. One thing is here that we have already used the data to estimate our decisions. And then we need to evaluate these estimates, basically. So we need to think about this, and that's why you can use cross-validation or something else. And yeah, so that's... So it's not, and another thing is, in the classical ranking and selection literature, you just have IRD things. The thing is, we influence, or covariates are quite influential, like in pricing, your data set, yeah.
Are biased.
If you look at your prices, how much variation do you have? It can be that you can ensure that the quality of the estimates of the simple model are very good, but not of the complicated model. If you do pricing with, say, a parametric or a non-parametric demand model. So there are all kinds of complications that can arise, especially if you want to do this dynamically. Because what do you want? Do you want a decision that is good, that helps estimation in both models, or only in the simple model?
Yeah, it's kind of generalization of this exploration context. I mean,
yes.
Yeah.
You put a kind of meta level above it, and then
yes.
you torture yourself. Okay, then enough torture. I want to share something we have 12 minutes left that I also find interesting. Namely, policy design can mitigate modeling errors. And I want to share 2 papers, which very briefly, which show this. And the first one is by Vespes and Zevi from 2015. And it's called On the Surprising Sufficiency of Linear Models, something like that. They say, well, we consider pricing with learning, sufficient inventory. The true demand function that we don't know, lambda, is nonlinear, possibly, with some assumptions. For example, we want to have a unique optimal price. But we, that means the decision maker, assumes it is linear. Now, is that the problem or not? Now, it depends. There are bad policies, for example, with fixed exploration prices at fixed time periods. Then you get linear regret. But in this paper, they say, well, sometimes it doesn't matter at all. So they present a policy, and the policy is as follows. So you just have some estimated optimal price. You charge that for a while, 2 to the power I. And then you do a small perturbation and you charge that price for a while, 2 to the I time periods. Then you have data at 2 price points. You do linear regression. You compute the corresponding optimal price, alpha divided by 2 beta. Okay, you need to project on your feasible interval. And that's the price for the next cycle. Now, this is a policy that you can motivate by a linear demand model, especially this part. You estimate a linear demand function. Now, and if you tune everything correctly, and lambda is not too strange, then the regret is still asymptotically optimal. Now, it's a nice result. It shows that in this case you are lucky. Now, why is that in this case? So we have we charge 2 prices, some p hat and some p plus delta. Now, then we estimate the slope and the intercept of where we just fit a line to 2 points. Now, they have particular forms. Then my next price is the estimated optimal price, alpha hat divided by 2 beta hat. Now, if you neglect the noise terms, which eventually will not influence the expressions, you get what you roughly get. So my estimated optimal price is roughly this. No. So if you converge, then the left-hand side should be the right-hand side. And by some rearrangement, then your price should satisfy this equality. Now, and then by some small rearrangement, I get the first order conditions. Revenue is price times demand. So if I take the derivative, I get this expression. So if you converge to a price with this policy, then you have to converge to the optimal price. Now, that's nice. And then the second part is you want to show that you do converge. And they show that by showing a contraction property that the distance, it's a dynamical system, the distance to the optimal price is at most some small gamma times the previous distance plus terms that are sufficiently small. Now, so in this case, especially this part, yeah, it takes some time, at least for me, it took some time to understand what's going on here. Why on earth is it the case that the limit price suddenly satisfies the first order conditions of the non-linear model? But I think that's a nice observation. Now, so basically the policy design is such that you can make modeling errors. In this case, you assume linear, but the truth is non-linear. Well, it doesn't matter. Another way of seeing this is the following. You have a demand function which is non-linear, but in the end, you only care about the optimal price. Locally around the optimal price, of course, the demand function is roughly linear. So yeah, you know, locally your model is good enough. And if you make sure that you converge, well, then things work out well. Now, very briefly, I want to mention another example. This is from a paper by with Boer Keskin. In this case, so in the previous case, you could say, well, you could also have designed a policy that accommodates nonlinear demand functions, just you have to work harder. But in this case, it's different. So we do dynamic pricing with reference effects. That means that the demand, it's not just, say, a linear demand model, but there is a reference effect. If my people have a reference price in their head that influences the demand. If what they believe is a fair price is actually more than the actual price, then that leads to more demand. And if it's more expensive than what they believe to be a fair price, then that leads to less demand. Now, there is empirical literature on this effect, a lot actually, and usually these eta plus and eta minus are not the same. The loss aversion case means that the difference by the same magnitude, if they are disappointed, then the demand is diminished more than the demand is increased if it's a positive surprise. That's how usually human beings work. Okay, this happens. So you can think, well, okay, we want to do pricing and learning. Small problem. It's not that this reference price here, is observable or published in a newspaper. You don't know it. You can assume some model. Exponential smoothing is often assumed, but you have no idea. Who knows the reference price? Who knows how it evolves, how it depends on the price history? Nobody knows. So what are we going to do? Well, we're just going to ignore it because, yes, it's in any case extremely difficult to estimate. We're not really going to ignore it. We're going to construct a price policy that diminishes the reference effects. How do you do that? We just keep our price fixed during long time periods, because then people will get used to this price. The reference effect will disappear, and we can just use or misspecified model without reference effect and hope for the best. So we use this same geometric cycle policy where you keep your price fixed for very long time periods. We compute our regret. We compare it to the optimal price path if you would have observed the reference price. If you observe the reference price or benchmark is quite strong, then the optimal price is not fixed, but there's a kind of price path. If you compare it to this unreachable goal, we still have an asymptotically optimal policy, which is nice. So what is the high level idea here? We have some complicated parameter. We have no idea how it behaves. We cannot really observe it. We don't even know if it's identifiable, all these parameters. So we just try to diminish its effect by our policy design, and then we can get away with our modeling error. Well, I think that's a nice conceptual idea that perhaps is also applicable in other settings. Okay, that's what I wanted to share with you.
Just a quick question on this. So,
yes.
So can you combine the two papers in the sense that, assume that the demand also, original demand is not a linear plus?
Yes, that's a good question. I think you can. We haven't done the analysis, but I think indeed, I don't see why you cannot do both. So, and there are reference effects that you ignore, and there is some non-linearity that you ignore. Maybe there are even more things that there's a lot that you can ignore with this policy, and still have a good performance, I think.
I see. And okay, did you think about scaling the reference effect as well, or so the eta plus and the only thing that I was thinking is that for a lot is kind of like you want people not to forget a little bit the last change, right? But suppose I tell effect factor is stronger, right? As you
Yes.
As you wait longer, the reference effect gets stronger as well. So kind of
I see.
You want to force it to stay in the limit.
Yes. Yeah, then you're dead. I mean, you're not dead, but this works because okay, so there is exponential smoothing. If you use exponential smoothing, then if you keep your price constant, the reference price will converge very quickly to this price. Now, we assume, we don't assume exponential smoothing, but we assume something. We assume that if your price is constant, then your reference price will converge sufficiently fast to your fixed price. But if you do not converge, then it's different. Now, what is interesting? So you keep your price fixed. If the reference price converges sufficiently fast to your price, then you diminish the reference effect. Then you're okay. The other extreme is that the reference price is just constant. But then I think you're also roughly okay, because then you just have some fixed effect. Okay, you have a kink in your demand curve, but other than that, you can accommodate for that. But the most difficult setting is where if you keep your price fixed, your reference price will converge, but very slowly to the price. That is, that's an open case. I don't know, maybe then you cannot get like square root t regret, but it's just, then it really influences your performance, I guess. Nice question. I think Yuri also raises his hand.
Yes, it's actually a quick question, also related with the reference price. So since the reference price encodes some dynamic about past prices, what if you also include in the demand the history of past prices that you had, and you try to model that with something that's non-parametric or something like that? But the idea is that the demand is a function, let's say, of the 10 time periods of prices that you had. Or no?
Yes, yeah, you can do that. I think there is a working paper by Abbasi. There is a working paper by, I forgot the exact name, who did that. So the reference price, so basically the demand is a function not of today's price, but of the last 10 prices. So you can do that. The problem is, why 10? Maybe it's actually 11. In fact, with exponential smoothing, it's actually infinity, although the effect becomes smaller. So you have this issue, and optimization becomes more complicated. But it makes sense because, well, maybe it's possible, especially for more complicated models. If you can measure this, it gives information, so why not use it? So I think in general, if you can measure it, then it's good to do that. But if you say, well, I have really no idea, then this is a possible workaround. But otherwise, that is a good idea, I agree.
Okay, thank you.
Okay, so we are at the end today. Let me see. So here's the summary. I'm not gonna repeat it. As before, the references are at the end. The slides will be uploaded. Next lecture is in a week, again at the Thursday. Then there are two topics. I will mostly talk about assortment optimization with demand learning instead of pricing. And briefly, I will discuss some topics in contemporary research, what people are doing nowadays. Not exhaustive overview, but some things that are interesting, I think. So that's it for today. I hope you enjoyed it. And if there are any questions, feel free to ask.
Any questions, guys? Thank you very much, Arnoud. Have a great evening.
Yes,
and we'll see you next week.
You too. See you next week.
Take care. Bye.
Thank you. Thank you, guys.